So let's talk about section 3.4, which is all about piecewise function and absolute value functions. We're going to learn how to evaluate and define what piecewise functions actually are. We're also going to take a good look at those absolute value functions and equations. So starting with piecewise functions. Piecewise functions are sometimes defined as functions in pieces for each interval of a domain. Now that sounds a little strange, but what we mean by this is start with just function notation. One of the things that we know about function notation is we define a function as for every input there's exactly one output. So in my case here, for my input of any x, I have an output of 3x plus 2. Now, what my output is going to depend on is basically what my x value is. So with that being said, with a piecewise function, you're still going to see that function notation, except for now you're going to see this thing called a brace. Now the brace is going to be quite large because it's going to contain at least 2 or more pieces. So it's not piecewise unless it's got 2 pieces or more. It can have more, or it could only have 2. Majority of the time you're going to have more than 2. So, but it could be something like 40, and we're going to say that 40 is only going to work when x is less than or equal to 0. And then we're going to have something like 2 plus x, and that's only going to work when x is between 0 and 4. And we'll let it equal 4 here. And then we've got our last part, which we'll let it be x squared when x is greater than or equal to, say, 5. Okay? So this would be basically a function. What we want to notice here is that there are 1, 2, 3 pieces, and each piece is only defined for a very small group of x's. So for 40 is only when x is less than or equal to 0. But notice I said it has to equal 0 here, but it cannot equal 0 here on part 2. So at part 2, I could be equal to, say, 1 or even 0.5. That would be included here, but I'm not going to equal 2 itself. Now I'm going from 0 to 4 on this piece. Now I am going to equal 4 on this piece, which means, again, as long as I equal 4, I'm here. And then I have x is greater than 5. Now you'll notice I went ahead and chose another number besides 4. It doesn't have to be the exact same number here. Majority of the time for conveniences while you guys are learning it will be, but these are not always going to be the same number. So that would mean something like 4.5 is undefined because there's nowhere where it's defined here in the domain part. But as long as I'm somewhat equal to 4 or less than it or bigger than 5 or equal to it, I will have basically a function to be defined as it. Okay, so let's look at some real-world scenarios with this. So our first example is the postage paid for a first-class letter jumps 15 cents for each ounce after the first ounce, but does not increase until the weight is increased by 1. So we're going to look at the following table, and it's going to give us what would be the postage for letters up to 3.5. And what we're going to do with this is we're going to write a piecewise function defined by this table, and then we're going to graph it. And we'll do the graph on the next slide. So what we see here in our table is that we start off with a 55 cents, and then 15 cents increases for every single ounce added here. So notice I go from 0 to 1, and then from 1 to 2, 2 to 3, and 3 to 3.5. Notice that at 1, I'm equal to 55 cents, but at 1 here, I'm not equal to it, so it has to be something like 1.1 for that one to work. Okay, so with our piecewise function, we can name it anything. Since I'm dealing with postage, let's call it P of X. And I'm going to have 4 pieces to it. So we've got 55, 70, 85, and 100. And then those are only going to work if x is between those numbers that we've defined already. Okay. Now, sometimes you're going to see this part right here where it says if. Okay. And sometimes you'll see that if as a comma. And sometimes you'll see that if as the letter if. It doesn't matter. Or as the word if. It doesn't actually matter which one you see it as. Now, to see this in a graph format, what's really cool about this is, remember, 55 is constant. There's no change with, like, if I'm just a half an ounce over, is it going to actually change out of 55? Absolutely not. So what we notice is that we have basically 55 from 0 to 1. Now you'll notice that at 0 it's an open circle, and at 1 it's a closed circle. And then my next part of it, it's 70, so again, straight flat line, and at 70 I have open circle, and at 80, or sorry, at not 70, at 1 I have an open circle, and at 2 I have a closed circle. But I'm 70 the whole way there on my y value. The next one is 85, and again at 2 you see the open circle, and then at 3 you see the closed circle. Now the open versus the closed circle is very important to note. Notice all of these that have the closed circle are on the sides that use the equal to sign. So a closed circle basically means that we are doing an equal to sign. Okay? So that's what we kind of want to pay attention to right there, is that all of those, that's why we ended up with it. So if I use this symbol here, or if I use this symbol here, then you need to use a closed circle. Okay? If I use, say, this symbol or this symbol, you need to use an open circle. Okay? And again, that's kind of where we can see that with these symbols here, that's why we use those. And then if you take a peek over on this side here, all of these had those kind of just like not equal to symbols. So any of these ones here, we use those open circles on. Okay, so now that we have an idea of what a piecewise function is and how it's defined, as well as what it looks like graphically, let's take another deeper dive into it. So let's say I want to graph this piecewise function. Now I've got two parts on this. The first part is 5x plus 2 if 0 is less than or equal to x, which is less than 3. And the second part, part 2, is x cubed if 3 is less than or equal to x, which is less than or equal to 5. So this is basically the same thing right here as saying I'm going to be a straight line from 0 to 3. I'll equal 0, but I'm not going to equal 3, so I'll have an open circle here. And then I'm going to use the graph for x cubed, but only between 3 and 5. I'll equal 3 here, and I'll equal 5 here. And again, when I say equal 3 and equal 5, I'm only talking about the x values. That's not going to tell me exactly what the y value actually is. So in order to construct our picture, it's sometimes helpful to make mini tables. So we've got two parts, so we're going to make a table for part 1 and part 2. On part 1, I'm going to do the numbers 0, 1, 2, and then I'm even going to go so far as 2.99. Now you can do 3 itself, but again, you have to be very cautious here. And remember, on this one, when we are taking a peek at it, what we do know is that this one here cannot equal. Okay, so it cannot equal 3. So the x value itself cannot. Don't care about what y value comes out. Okay, but I do see again that it is somewhat of a straight line as I'm working myself there. Now on the second one, I noticed that it's x cubed. Now what's really cool about the x cubed is x cubed looks something like this in its base format. I have a place where I can actually equal 3 and I can equal 5, so those are both perfectly allowed. And so when I plug in x equals 3, I'm going to get 3 cubed, which is 27. And when I plug in 5 cubed, I'm going to get 125. Now we're going to put those two different pieces together. And so when I put the two different pieces of the graph together, we're going to have that straight line part of the graph there. And that's that first part 1. And again, noticing there that we have the open and closed circles. Okay, again, closed circle on 0, open circle on 3. But then notice at x equals 3 and all the way to x equals 5, we're using that x to the third. Now remember, this graph, if I were to graph all of this in my graphing calculator, it would look something like that. So again, this is not the whole graph that we're seeing. We're only seeing that one little part for when x is between 3 and 5. Let's try another one. So let's do wind chill factor. Wind chill factors are used to measure the effects of the combination of temperature and wind speed on human comfort by providing equivalent air temperatures with no wind blowing. One formula that gives the wind chill factor for a 30-degree temperature and a wind with a velocity of v in miles per hour is the following. Now, W is going to be our wind chill, and v is the velocity of the wind. So how fast is it actually blowing? So as long as the wind is only blowing between 0 and 4 miles per hour, it's going to feel like it's 30 degrees outside. However, if it's between 4 and 55.9, so we're getting a lot more wind there, that's going to change, and it's going to give us a formula that we need to plug in to see like what comes out. Now, the third part is that, well, if that velocity is greater than 55.9, so say 56 miles per hour, then we know it's going to feel like it's negative 6.5. Okay. So let's find the wind chill factor for the 30 degrees Fahrenheit when the wind is 40 miles per hour. Now remember, 40 miles per hour is the middle part of that expression. So we're going to use that middle part of the expression, plug in 40 everywhere we saw our v, because that's what v equaled, and you're going to simplify it out. And we get about negative 5.091, which would be approximately negative 5. So if it is actually measuring 30 degrees Fahrenheit outside, but we have a wind blowing at 40 miles per hour, it's actually going to feel like to my human body as if it was negative 5 degrees. Okay. Let's try part B. Part B asked for find the wind chill factor for 30 degrees Fahrenheit if the wind is 65 miles per hour. Now, with 65 miles per hour, that means that we're using that third part of the function. And that's going to be where we have that velocity is larger than 55.9. Since that is larger than 55.9, it had nowhere for me to plug in the velocity. It just said it's going to feel like it's negative 6.5. So this means that with a 65 miles per hour wind, a 30-degree temperature would actually feel like it's negative 6.5 degrees. Now, let's look at the graph of this. Now, with the graph of this, what's really interesting and cool is when you graph it, you're going to see this kind of strange straight flat bit here, and that's that 30 degrees. Remember, from 0 to 4 it was completely flat, and then right here is where it actually starts to get kind of like just this decrease of, we go from 30 degrees to something really, really cold very quickly. But then it looks like it straightens out. So at about 55.9, which would be somewhere around here, it ends up becoming just perfectly straight, and it will be that negative 6.5. Now you'll notice that there's no open or closed circles here. And what's really cool about this one is because there's no open or closed circles because of the fact that the beginning and end on both of these end up being the same number. So there's no need for like a open and closed circle for a disjunction. We use the open and closed circles so like if they end up being two different places, then I know like, okay, this is where this one equals at x and this one doesn't. But when they both equal the same number, it's a very easy transition into the next one, and you don't need an open or closed circle there. Okay, so that's the graph. Now part D is asking for what is the domain and range of this function. Now, if we take a peek back there, we can very specifically say that the domain of that function was from basically 0 to about 70 is what I would say. Now, when I say about 70, what I'm talking about there is that it's 70 miles per hour. Notice that it does technically go bigger than 70 miles per hour because, again, I didn't limit it on the piecewise function, but by the graph that kind of showed you kind of where I had. But we did see that we only had a wind chill or a temperature that started at 30 and then it got progressively smaller until it was about negative 6.5, and it didn't go anything below negative 6.5. Okay, so let's try this again. And again, remember, piecewise functions are very practical because they are stuff that we see pretty much majority of the time. So the cost of a weekend service call by AirTech Services is shown by the graph below. Write a piecewise function that represents the cost for service during the first 5 hours defined by the graph. Now, the first thing I begin to notice is that these are perfectly straight lines, and I notice that here it's perfectly 330, here it's 550, and here it is 770. I know that this works between 0 and 1, this one works between 1 and 2, and this one is here from 2 to 5. Okay, so since we see that there are 3 pieces, we're basically going to make our 3 different functions, because they're constant, because they're straight like this, there's no variable, there's no rise or run, like it's perfectly straight, then each one of these is going to equal that exact number, and then we're going to put it from 0 to 1. Now notice here that I'm not going to equal 0, but I am going to equal 1 for the time there. And then for the second one, again, I'm not going to equal 1 because it's open circle, but I will equal the 2. And then on the third one, I'm not going to equal 2, but I am going to go all the way to 5 and equal the 5. Okay, another function that is actually a piecewise function is called the greater integer function. Now, the greater integer function is basically defined as the greater integer less than or equal to our x value. So, for example, if you have, what is the greater integer of 5.8? Well, that would be 5. The greater integer of 7 would be 7. The greater integer of a negative 4.7 will be negative 5. Okay, the greater integer of negative 9 will be negative 9. Now this seems a little strange, and I know a lot of people kind of struggle with it, but the greater integer function looks something like this. Now it can be graphed in the graphing calculator. This is one that we will not specifically use in this class here, but I do want to make you aware of it for those that are moving up into the higher level math, because it is one of those really cool just piecewise functions that kind of make its appearance. And what's super cool about it is it basically takes any number and rounds down to the nearest integer. Okay, because that's the last full integer it would equal before it moved up to the next one. Okay. So let's talk about absolute value equations. Now this is extremely important. This is not a formula, this is a method, which means you're probably going to want to write this down somewhere and kind of memorize this idea. But what it says is basically if you have the absolute value of something and it equals a number, and that number we know is positive, greater than 0, then what's inside those absolute value bars will actually equal that number or equal the exact opposite of that number. Now, there is no solution if we happen to have the absolute value of our thing equal to a number and that number is, say, negative, then that cannot happen and that would be no solution. Or you're going to have one solution when the absolute value of our stuff is equal to 0, then that stuff must just equal 0 because you don't have anything positive or negative for it to be. So let's put this into play. So we'll start with the first one. And what we want to do is we want to start by saying, okay, I have the absolute value equals a number. So therefore, all of the stuff inside, so all of the stuff inside here will either equal 9 or negative 9. Notice I have not changed anything inside those absolute value bars. It's very important to note that what's inside those absolute value bars stays exactly the same. So now they're linear and I can just add 3 on both sides there, and we're going to get x equals 12 or x equals negative 6. And then that's it, you're done. And that means with absolute values like that, if they equal a positive number, there will be guaranteed 2 answers. So we'll do it again with part B. And again, the same thing is going to happen with part B here. You have the absolute equals a number. So again, I'm going to take that absolute values, and whatever's inside here is going to stay exactly the same. What's on the outside is what I'm going to equal to positive version of it and a negative version of it. And then we begin our solving. So again, just take each one separately or both at the same time. So you're going to add 4 to both sides, then divide by 2, and we get x equals 6 or possibly x equals negative 2. But again, both answers, there's 2 answers here, both of them need to be included. Do not rule out a negative x equals just because you can't do that. What's happening is that it's basically saying that if you take the absolute value of, say, negative 5, my answer is 5. But if I take the absolute value of 5, it is still 5. So what we're saying is if I have the absolute value of x equals 5, this thing in here can be either one of those negative 5 or positive 5. And that's what we're doing here, is we are saying that all of that inside either equals the positive or the negative version of it, which means basically that I'm going to have to do a little bit of solving for what x will make it that positive or negative version of the number on the outside. So let's talk about, again, another example, but this time let's make that inside a little bit more complicated. Now, here's the thing. I don't really care what's inside the absolute value bars. That's actually not the important part. What's important is what is on the outside of those absolute value bars. One, I want to make sure that there's nothing that's being multiplied, divided, added, or subtracted to the outside of the bars. Nothing's allowed to change what's inside the bars. But once we've made sure that the bars are isolated by themselves, then I want to pay attention to that number. Now, if that number is just a plain old 6 or 7 or 20 or 15, I really don't care as long as it's positive. If it is positive, then we can say, okay, well, all the stuff inside equals 6 or all the stuff inside equals negative 6. Now, at that point there, hopefully you began to notice that this problem had these beautiful powers of 2. And anytime we have things that are power of 2, that makes it quadratic. So since we had x squared, we are now in the realm of quadratics, which we learned earlier. And we learned that to solve those, there was a couple of different methods, but one of the best methods was to start by making one side 0. So we're going to basically, on this one over here with the positive 6, we're going to subtract it over, make it equal to 0. And on this side here with the negative 6, we're going to add it over and make it equal to 0. Once we are here, we have 2 options, okay? We can use our very different methods here. Now, if you can factor, that would be great. If you cannot factor, then you can use a quadratic formula. So mine happened to factor very nicely, set each factor equal to 0, and I'm going to get x equals 6 or negative 1. And in the other option, I got x equals 3 or 2. Now, this does mean that because it's x squared, that means there's 4 possible answers here. You will have to list all 4 of them. And that's how we solve absolute value equations.